Class, today we are on chapter 4.2, the natural exponential function. This section is very similar to the last section, chapter 4.1, in which we talked about the exponential function. So at the end of the last video, we're talking about compound interest. And what we noticed is that as the number of times that we compound our investment in a year, that the amount that we receive back in interest increases. Okay, so this was the function that we were using, right? 1 plus some amount, right? So since this is larger than 1, it'll be an increasing function, which is what we want when we invest money, right? So what we noticed again is that as we compounded more frequently, right, as our value n here went to infinity, got very large, the amount of money that we invested at a set percentage rate of growth, in our last video was 0.5%, for a set amount of time, it was 5 years, right, was increasing, right? So if n was increasing, then the amount that we were getting back was increasing as well, but it only increased to a certain value. It didn't go to infinity if we kept the time set at a value and the investment rate set at a value. Our investment didn't grow to infinity, it kind of started to level out somewhere, right? So in order to explore this more, since P, R, and T were all sort of set at a fixed rate, right? It was 0.5%, 5 years, $2,500. What we're going to do here is let's let all of those values be 1, okay? So we held P, R, and T constant before and only changed the compound rate, right? The compound amount per year. So we're going to hold P, R, and T fixed at a value of 1 because we know 1 never sort of affects things when we're doing mathematics, right? As far as multiplication and powers go. So we're going to fix those at 1, and so our formula will look more like 1 plus 1 over n to the n, right? So we're saying we're investing $1 at a rate of 100%, I guess would be the case. And the time is at 1. So everything is just kind of set, and we're just going to look at the 1 plus 1 over n to the n. We're going to see what this does as n increases, okay? Because as n was increasing before, again, we sort of approach this singular value for our situation. So when n equals 1, we have 1 plus 1, right? 1 over 1 is 1, so we'll have 2 to the first power, which is just 2. When n is 2, we have 1 plus 1/2 squared, okay, so 1.5 squared, which is 2.25. I'm not going to go by ones because this will take a very long time because we want to have very large values of n. But again, notice that minimum, I'm going to have 2 for this thing, right? So when I plug in larger and larger values, so this time let's go to 10, I'll have 1 plus a 10th, right, raised to the 10th power, so 1.1 to the 10th. It's 2.59 and some change. So let's add another 0 and make this 100. Right, so we've jumped up from 1 to 2 to 10 to, let's say, what happens after compounding 100 times in a year, for instance, right? We have 1.01, so again, 1/100th, so our 1 is in the 100th place, to the 100th power is 2.704818329. Okay, let's go to 1,000. So we have the 1 plus 1,000th to the 1,000 power. Right, so 2.71. So as you notice, it's starting to stabilize a little bit. I had 2, so all my values are still 2. The second decimal place was 2, 5, 7, and then 7 again. So it's starting to sort of approach a value, right? So for my next value, I have instead of 10,000, we're going to go to 1,000,000, right? Let's just kind of expedite this a little bit. So that looks like this when I plug it in. I have 2.718280469, right? So the 7 and the 1 were the same from the previous iteration, right? And then I have some other values that are different from the previous value we plugged in. So I'm starting to stabilize towards a value. It's not increasing without bound, as we say, right? It's not just going to infinity, right? It is getting large, but it's starting to approach some value, okay? if I put in 10 million, 2.71828. So you see how I have several values that are the same now, and it's only slightly different than the previous value when I plugged in n was 1 million. So we're stabilizing towards a value. Okay. So the value that we're stabilizing towards is our value e, the natural base. So as n goes to infinity, 1 plus 1 over n to the n stabilizes to the value that we call e, which is 2.718281, yada yada yada. So this is our value. Okay, and notice we were very, very close. 718281281, and then the real value is 8, and then 28. So we were accurate all the way up until this point when we plugged in n was 10 million, right? So very, very large value. So if we went to the billions, gazillions and all that kind of stuff, trillions, quadrillions, and start plugging in even larger and larger numbers, we're going to get closer and closer to the true value, but maybe we would get up to like this decimal place of accuracy, and then everything else would be wrong. Okay, so as we get closer and closer and closer, larger and larger values of n, we get closer and closer and closer to the real value, which is this value of e. Okay, now e is an irrational number, right? It's just like pi. It goes on forever. It does not repeat. There's no pattern to it. It just continues on forever and ever. Okay. So notice again that when we had 10 million, we were accurate to 6 decimal places. 1, 2, 3, 4, 5, 6. Okay. So we're accurate to this, and everything else after that was off. So at this 8, we actually had 6, right? 1, and then was 693. So we were very, very close. Okay. So we were close. We're accurate to the 1/1,000,000th value, right? That's how accurate we were. So very, very, very accurate. So this is the symbol for the irrationals. It's the real values minus the quotients. Okay. So an irrational number, it's all real numbers except for all of your possible fractional values, and that's our symbol for irrationals. Okay. So we call this the natural exponential function, or the natural base, right? So then the natural exponential function is an exponential function where we use e as the base. Okay. So f of x equals e to the x. So again, remember, very, very important, e is not a variable. It's not some unknown number. It would be like if I wrote pi to the x. It's an actual value. It has, we know pi is related to circles. E is related to exponential functions, right? In the way that we just calculated. Okay, so remember, e is a value. It's a number. Okay. If we have a compound interest situation where we compound continuously, that's what we're doing here. What if we are always compounding our values, right? So there's no time frame where our interest is not being accrued, right? So it's not every month or every day or every second even. It's always, right? If that's always happening, we use the exponential, the natural exponential base, right? So it's for continuously compounded situations, okay? Things like exponential growth, right? When things are continuously growing at an exponential rate, that would be a continuously growing or continuous base situation. Okay, so since our base is continuously growing, our continuous compounding function turns into p e to the rt. I always remember it as PERT. Same thing, r is my interest rate, right? T is time, and p is my initial value. So if we use the same example that we had in the last video, where we're investing $2,500 into a money market account that has an average return of 0.5%, okay, but that's being applied continuously instead of yearly or monthly, right? How much money are we going to have after 5 years? So it's very straightforward. Again, we just plug in all of our values. 2,500 exponential base raised to the 0.005 times 5. Okay, so it looks like this after I do a little bit of math. And it comes out to $2,563.29. This is very, very close to what we had when we, in our last video at the end, when we used n equals daily, right? So it's a little bit more than compounding daily, obviously, because we're compounding continuously all the time. But the value is very, very close. Okay, so after 5 years, we would have earned $63.29. So next we're going to talk about hyperbolic functions. Not all of them, just two actually. So hyperbolic functions are defined with the exponential base e, and they're very, very similar to trig functions, except that they're not related to a circle, they're related to a hyperbola. Okay, so the hyperbolic functions are related to a hyperbola the same way that trig functions are related to a circle. So there's analogous functions for the hyperbolic functions and the trig functions. If you haven't gone through trig, then don't worry about it. We're going to cover trig in the next chapter, chapter 5 through 7, I believe. But you don't need to know any trig in order to do what we're about to do now. Okay. So the two most basic functions in trig are the sine function and the cosine function. And so for hyperbolic functions, we have what are called hyperbolic sine, or sinh, right? With this H, it's actually called sinh is how it's pronounced. And we have hyperbolic cosine, which is related to cosine in the trig functions, and we call this cosh of x. Okay, so my sinh and cosh functions are defined as such. Okay, sinh is e to the x minus e to the negative x divided by 2. Cosh is e to the x plus e to the negative x divided by 2. Very, very similar, but one is plus and one is minus. Now notice that I can separate this into two fractions as 1/2 e to the x minus 1/2 e to the negative x, right? Or I can distribute this into two fractions as well, 1/2 e to the x plus 1/2 e to the negative x. So the only reason that's important is because we're going to look at the graphs of these, and we're going to break this down into their two separate functions for sinh and the two separate functions for cosh, right? So if I have 1/2 e to the x, notice that I go through the value 1/2, and it's a growing function because the exponent is positive, right? It's not negative. So e as well is larger than 1. It's 2.7 something something something. So it's an exponential growth situation. Negative 1/2 e to the negative x, right? So we have some transformations here. The negative 1/2 is going to flip over the y-axis, I'm sorry, the x-axis, and the negative x portion is going to rotate us across the y-axis. So we're flipping over the x-axis and across the y-axis. So it looks like this. So remember, for sinh, I subtract these two things, or I'm going to add them actually, right? I have the 1/2 e to the x and then minus 1/2 e to the x. So if I add the minus, I'm taking the 1/2 and I'm taking the negative 1/2, and then if I add those together. So if I add 1/2 and negative 1/2, I'm going to get 0, right? If I add this value and this value, it'll still be negative, but it'll be over here, right? Here's more negative, here's this one. So if I add these together, I get my sinh. So my sinh function actually looks like this. Okay, it's a curve in this form. If I do the same thing for cosh, okay, remember cosh was 1/2 e to the x, and a positive 1/2 e to the negative x, right? And I'm going to add those together as well. Okay, so 1/2 e to the negative x is going to rotate this across the y-axis, right? And if I add those together, I will get what? So 1/2 and 1/2 will give me a 1, right? This value and this value will be a little bit larger. So I'm just going to increase in value, and so this is what cosh is going to look like. Okay, so that's what sinh looks like, and that's what cosh looks like. And they're functions that are made using the exponential base.